Alright, let's go ahead and get started. So I'm going to be talking about Agda, and just what is Agda? It's kind of a split. On the one hand, it's a dependently typed functional programming language, and you can look at some of those like particular features that it has. This is all from kind of an old wiki. On the other hand, it's a proof assistant. It's research grade, so we're talking, nobody runs any Agda programs in production or anything like that. And it's typically used as kind of this weird thing that's right between the two, because it isn't really geared toward proofs exactly, and it's not exactly geared toward functional programming, programs that you can run, like creating a web server or something like that in Agda. So what it ends up being is really like a theory, Martin-Lof's type theory, that looks like programming, looks like Haskell, and that you can encode proofs in there. You can do mathematics. You can do all of Benjamin Pierce's software foundations proofs for Coq in Agda, and you can also do programs that look a lot like Haskell, and then start to encode invariants and proofs and start to pass around that information. And that's kind of what we're going to do today. Running a functional program is effectively normalizing or reducing a big expression into some smaller one, and that is how we're going to run it. We're going to be creating, we're going to follow this paper more or less, and kind of simplified a lot of the code. This is actually a literate Agda file, so it's written in Tech, and then with embedded Agda here and there, and so you can actually look in GitHub. If you go to my repo down here, you can scroll down at the bottom, the resources. You can look at that PDF itself. If you go here, you can see his code that he put on GitHub. And I go like, this is the actual paper, for instance. And then somewhere down in here, there's like these begin code sections that are the Agda code. So what we're going to do, what this paper is basically about, is how to create a binary search tree that is correct by construction. And then he does this crazy thing where he creates this universe of like this generic programming thing where you encode like all kinds of like the basic Haskell data types or something, and mapping that into like an ordered universe of data types, and then sort of like basically any kind of like binary search tree like structure you want, and then implementing 2-3 trees on top of that with the invariant of 2-3 trees baked in. So everything is correct by construction in the 2 and 3 section, and I'm going to simplify that. So what we're just going to do in part 1 is kind of get used to how Agda works and write a basic binary search tree in simply typed Agda. And then part 2, we're going to bake in the invariant in a binary search tree, which I'll explain in a bit. And then, depending on how much time we have, I'll either live code 2-3 trees for you, and then with the invariant baked in, so correct by construction, or I'll point you around in the code a little bit. And if we even have a little time after that, I'm not known for being ahead of time on schedule, but I can show you a little bit about what the universes look like at the very end. So part 1, just a refresher of binary search trees, or an introduction if you're not familiar. It's a tree with nodes, so a node will have 2 children, and then a leaf node, represented by the square boxes here, don't have any children, and you can store whatever you want in there. In this case, we're going to be just storing numbers, and the invariant is that every value on the left subtree is less than or equal to the value in a node, and every value in the right subtree is going to be greater than or equal to the value in that node. And so that's what we're going to be doing. But first, so if you all have Agda installed, you can follow along, and I'll be live coding, so you should be able to kind of follow along and get the sense. There's kind of this environment of Agda, the way Agda works with Emacs in the Agda mode, that's really, really nice, and it's I wouldn't recommend writing Agda without it. So the way you, Agda is like a core theory, so you don't have any data types off the bat. So if you suffer from not invented here syndrome, and you really like precision, then Agda is a great language for you, because you can create everything the way you want it in this particular theory, and it's really rigorous. There's no like bottom inhabiting every type or anything. It's like if a type's uninhabited, it's actually uninhabited. So it's a very faithful implementation of type theory. So just to get a taste of a type, we're going to create a type for bool. The word set is used everywhere for type, so I'm going to use those interchangeably, probably mostly calling them sets because that's the keyword that's used there. I wouldn't worry. You can talk about what the distinctions are, but I'm not going to worry about it for this talk. I'll use them interchangeably. So if you're familiar with Haskell, the GADTs, everything is in GADT sort of syntax. So the idea here is true is a bool and false is a bool. So we have given two values for a bool. And if you want to create some variable, you can say it has type bool, and then you have to say equals and give a what value. If you type a question mark, then that allows you to create a hole. And Agda, when you write Agda, I'd highly recommend using holes all over the place. So the first keystroke that you should memorize very well and use all the time is Control-C, Control-L. So what that'll do is load and type check the file, and if you have a question mark representing a hole somewhere, it'll put this cool little thing. And down at the bottom, it'll tell you, hey, hole 0, they'll be numbered, is of type bool. So you have to type an expression in here of type bool. And we only have two ways to do that right now. And you can do this -L and then do Control-C, Control-A, and it'll say, you can ask it, it's sort of like asking, hey, what can I fill in this hole that will be of that correct type? And Agda say, hey, you can stick in true or you can stick in false. So if you type a value and you want to fill it in the hole, you used to do Control-C, Control-Space. There's a lot of different syntax, and I'll kind of repeat them as I do them. If not, just ask me and I'll say what I'm doing. But the main one is Control-C, Control-L, because that will load the whole thing. So there, that's how you create a value. Pretty straightforward. If you want to create a function like not, which if you give me a bool, will return a bool, you can write it in a pattern matching syntax like this. So not of some bool here. And you should return a bool. And so if you do Control-C, Control comma, that will give you this little thing down here. So now in this hole, it's telling us the goal is that we need to input something of type bool here, and what we have available to us, at least in the context of this line here, is an X of type bool. And this is another one I recommend keystroke recommending you type. So if you type the name of the variable over here, and you do Control-C, Control-C for case split, it will split it into the possible cases that you've defined, right? If you go back to where you defined bool, we have true and false, and that allows us to case split there. If you say false here, and then true there for that. Now, my bool can be any expression, right? And so now, if we do a Control-C, Control-L, and put the hole in again, we can type, not true, for instance, and fill that hole. And then there's another keystroke that's important to remember, because that's kind of how you run a program, or normalize. So if we take this expression, not true is going to kind of look up here and say, well, not true is defined to be false. So it's going to reduce down to false. So if you do Control-C, Control-N, where the N kind of means normalize, if we try to normalize, if we ask it to normalize my bool, then that will it'll say false down here. Can everybody see that, or should I try to move this up higher?
Probably, yeah.
I will pop out of full screen mode then and shrink the window. All right. So if you do Control-C, Control-N, then down here you type this expression, and you can either type in a variable like that you've defined, my bool, or you can type in something like not of false, and then that will evaluate to false. Okay. So if you want to define and, which takes two bools, then you can do it like that, Control-C, Control-L to load the file. And when you case split, you can give it two arguments. And when you case split, it will sort of give you all the possible combinations, which is kind of convenient. Or if you just wanted, if I did undo there and reloaded it, if I do Control-C, Control-C on one of them, then I can just do one side. And in this case, you can define and this way, right? Agda has a call by name evaluation strategy, so it feels like Haskell most of the time. So what's going to happen here is it's not going to try to normalize this what's underneath y. If you pass in and you give the second argument, it's really huge, and maybe it takes forever, a really long time to compute. In this case, if you go on this branch, it won't even look at it. It will just return that, and it won't normalize it until it actually. It's just like Haskell. It only try to normalize or evaluate an expression down to a value when you pattern match on it. So it's pretty similar to Haskell in that way. So here are some syntactic things. You can give names to these arguments up here because this is how you're going to do dependent types later. But for now, it's like just kind of a cute thing. And so there's a syntactic sugar that sort of suggests that curried functions are kind of like uncurried functions. So you can, if you use this parenthesis where you give names to each of the arguments, then you can omit the arrows between them. It's identical, it's just syntactic sugar. And there's further syntactic sugar that this is also equivalent to that. So more syntactic fun things. If you can do infix operators with anything at all, any combination of Unicode that are all kind of jammed together by putting underscores where you expect all the arguments to go. So now we can inline, we can say x and y equals something, and we can do the same thing. And you can do Unicode. I'm going to do ASCII throughout the talk, but if you look on the Agda documentation, if you type / and you type it correctly, you can get sort of the Unicode operator you use for and in logic. So you can do it that way if you like. All right. And oh, by the way, when you give names to things, it only applies to the end of the type signature. You have to give new names down here. The fact that I call this y has nothing to do with the fact that I call a y up there. Okay, great. So some other data types. Natural numbers. So a natural number looks like this. There are lots of ways to define numbers. This is a common one because it's convenient to prove things about. And that's really the main reason. It's about the most inefficient kind of representation of a number you can possibly imagine. Other than like singularly inefficient numbers. But basically the idea is 0 is a natural number, and if you give me any natural number, I'm going to give you back like the natural number, the next number effectively. So that's what successor is. You can kind of think of it as +1. The nice thing about Agda, since everything has to be separated by spaces, you can actually prefix things by numbers as long as the whole thing isn't a number. You know, whatever you separate by space. I can't do that, but I can do weird stuff like this. So that way, now if I have something of type nat, you can do, remember, if I type -l in there, which is kind of like an argument to this like mini program, if you do Control-C, Control-A again, that will sort of list different things you can put in there. And so this gives you examples of all the numbers, and you can keep on going and say, well, skip to 10 and tell me what's there. And it's like, well, you can, you can keep on asking it. You can just tell me like, well, give me the 10th one. So you can say, give me the 10th one. There. So that's effectively, I think, 10. Anyway, so the way you recognize a number is by looking at a term like this and effectively to yourself sort of counting the number of these +1s or successors there are in it. But that gets really tiring. So like that would be equivalent to 1, and that's equivalent to 2, and so forth. But Agda has this little sort of magic-y thing that Haskell, comments are just like Haskell. So if you do a built-in natural, and then you give the name of the type you've created here, and as long as the type has a signature just like this, then you can, instead of typing that, you can just type in 2. It's exactly the same thing, and there is no difference. This just allows us to view it like this, which is much easier to view than like trying to count the number of sucks that you're doing. So you can do like 10. And if you normalize to show it, it will also show down here the decimal form. Yes, sir?
How did you do the thing where it generated the like set of the
right?
That's the set of calling suck.
Yeah. So when you're in a hole, so if you do type question mark and do Control-C, Control-L to load it, and you go into the hole, you do -L is think of list all the possibilities, and then you do Control-C, Control-A to think of like autofill, and that will list different solutions to. Nice. Like if you think of it as a problem, then you need to give me something of type nat. Well, for really complicated things, like give me this proof of Fermat's last theorem or something. It's like, well, try to fill in what it can do, you know. And it's a very limited, and after 5 seconds, it'll cut you off and just try to say, well, I can find anything in 5 seconds. So.
And how do I pick one?
The if you do S and L together, you think of it like a command line argument, then S will skip, it will start, or skip or start, I don't know, start at number 10. So if I start at number, you know, I don't know, 100, I wonder what that'll do. It'll take a long time. So I just fill up my buffer with a lot of junk. Anyway, if you take off the minus L and just do minus S and then the number, that'll pick the 10th one right here. And we'll use that later.
So if you hadn't used that built-in natural,
yeah.
like what would the numbers like mean anything? If you just type 2, would it just completely not get it all?
Yeah, it would just be like, I don't know what a 2 is.
All right.
Yeah, and so I think when you tokenize, it tokenizes everything by spaces. It's a primitive tokenizer, but it's a very advanced parser. The tokenizer is really simple. So if you have a token that's just numbers, I think that's sort of reserved to be used in this way. So you can't give an identifier to that. I don't think I can actually call this 0. It'll be unhappy. You actually have to give it something that has a non-number in it. Yep.
I'm sorry, just what's the last step of that, like when I have 100 sucks in my buffer, or just 10?
Same thing, Control-C, Control-A, and that will
Control-C.
fill it, in this case, with that solution. All right, so now we have nats and bools. Is there any questions at this point? We're just kind of fooling around with syntax. So we're going to write, remember, binary search trees. We need to know whether 1 is less than 3 or not, so we need to write a less than or equal to function. And so for starters, we'll do it like this. Given 2 numbers that are natural numbers, we return a bool. So since we've encoded numbers this way, the way we check is we can case split on the first one, and we know that 0 is less than the other number, less than or equal to. If y is 0, it's 0 is less than or equal to 0, and if y is bigger than 0, then it's equal. So we'll say that's true. In the second case, we case split on y, and we're going to say, well, successor means it's 1 plus something. So 1 plus anything is never going to be less than or equal to 0, so that's always false. In this case, we don't really know, so we're going to recursively call that function for that. So if we do Control-C, Control-N to sort of test this idea out, say is 4 less than or equal to 5, we get true. Is 5 less than or equal to 4 or 3 or something? It's false. Okay? So let's define lists. An empty list, or nil, or whatever you want to call it, is just a list. And then we're going to create a little infix operator for the cons or adding case. So we're going to hard code natural numbers in here. I can show you how to abstract what that is, so you can do list of nats, but it'll be easier to do lists because all the trees and stuff will all be natural. If you really are interested, on the GitHub repo there's this modular file where I've modularized everything, so that way, sorry, the scrolling is really crazy over here. So for example, you can define list as a module, and modules are like namespaces, but they can also be parameterized by type. So, hey, given a list, it has a parameter p set, and so everything in here that's a function has this like extra argument, which is what set it is, or what type it is. So in this case, this will be kind of, to refer to a list of natural numbers, you have to say list nat, just like you would in Haskell or something. But if you're interested, this is one way that you can parameterize it. So if we have some other list, we're going to stick another natural number on the front, and that will return a list. So if we have my list, which is a type list, and we say, so we can have a little fun with the little solver and see like, hey, it can do an empty list. It can stick 0 on it. It can put 1 on it. It'll put 2 on it. Or like, well, we'll put 0 on it and then have another 0, and you know, and it is like fill in with random stuff because the space of that is of course very huge. But you know, we can do nil, and we can stick a 3 in front, and then we can stick a 6 in front of that, right? Oh well, right now we have to parenthesize it, so we can tell it this. I want this to be infix and infix r, so write associative and give it a number, which will help precedence if you have multiple operators like this. Then you're saying that is equivalent to that. This is equivalent to the parenthesized version I just had. Okie dokie. So let's create a binary tree. Binary tree is kind of a simple structure where we have either a leaf with nothing or a node that has 2 children. So it's kind of like the same sort of thing. Binary tree. So we'll have a leaf, which is just a tree, and then we'll have a node, which takes. Some people like do the left tree here, and then the value here, and the right tree here, and then that's going to be effectively a tree in the end. So if you give me 3 arguments, a left tree, a number, and a right tree, then we're going to give you back a tree. I'm going to push this to the left. There are different ways you can use like pattern synonyms and stuff later to like reformat stuff, but what's going to happen later is these 2 trees are going to be dependent on this, and so I'm going to try to just get you in the mind of thinking the node has a value, and this is a left tree, and that's the right tree. You can give names to stuff if you want, so you can call this the P, I don't know, and then remember you can get rid of the arrows if you're naming everything. So there's a left tree and a right tree. I'm using sort of abbreviated things just because when you start pattern matching, if you have really long names, the patterns get incomprehensible. All right, great. So we have a tree. So let us write from list. Takes a list of natural numbers and gives us a tree of them. So you give it an argument like x's. And then if we case split, type in x's and control C to case split. Then in the nil case, we'll just have a leaf, and control C, control space will fill it and type check that it's correct. So I typed in nil, like if I had a hole and I typed in nil here, it's like, yeah, you're trying to add something that's a list data constructor, not a tree data constructor. They don't. So in this case, we can, well, actually, probably want to go the other way first. Actually, that was what I wanted to do. We'll come back to that one. I could do this one, I guess. Sorry, I just had a little brain lapse of what I actually want to do here. So this is kind of what I was thinking. All right, so there's a big list of numbers. All right, let's create a tree. Let's create a tree first, just to get an idea of what the structure looks like. So you can create a leaf, and if you have a node, then you have to put like a number in there, like 3 or something, and then you have to give it the left tree and the right tree. So that would look something, well, not quite like that, but if these were both leaves over here, it would look like that. And then if we wanted to stick something on the left subtree, we can do that. And if you do, if you start a hole, you can type in the start of something, but like, I don't remember how many arguments node has. I know there's a node. What we can do is Control C, Control R, which will refine it, and then put holes for each of one of those arguments. And then so it'll tell you 0 should be a gnat, 1 should be a tree, and 2 should be a tree. So as your types get more precise, this becomes really helpful because you'll have stuff in the context, and you're like, I gotta put that over here and this over here. So we're gonna stick 1 on the left, which is what we did before, and then we have 2 leaves. So now we kind of have filled in this side over here. So the 3 has the 1 on the left, and then the right side we're going to put a node which has the 5 value. There. All right. So let's do a to list actually, and convert a tree to a list, because that's pretty easy to write. So if you have a tree T, we're going to case split. What are the different situations that we run into? Agda starts doing these like funky Unicode things. I never like the names that it really gives. So this kind of is a renaming thing. So we have node P, left tree, right tree. So leaf will be nil. A node will stick a P on the front. Well, so if you notice, what we're going to want to do is, well, if we call something like, we're going to call some function over here that we're going to do recursive, a to list on the left side, and then the left tree, and then we're going to want to effectively like append it to, you know, some kind of like list of P, right? P in front of nil to like to list on the right tree or something like that. So we're going to need to define some kind of append. I'll just use a name for it. So if we have 2 lists, we're going to return the list. So if we do have x's and y's, the case split on x's, if we want to append if the left side is empty, then we're just going to have the right side. Else we're going to stick X on the front of something, and so you can do Control-C, Control-R to kind of append, and then what you can do is just fill in here, just recursively append them until we hit the nil case. And then over here, it's like, well, I kind of wanted all this stuff, so really what I wanted to do is append two things, and appending on the left, I'm going to list the left case, and then on the right case, I'm going to stick kind of P in front of something, and then I'm going to stick to do a recursive call of toList on the right tree. Okay, how's that? Good?
Wow.
Kind of getting a feel for, at least when you're watching it, like how you can interact with it and kind of some of the things it gives you.
What are the like numbers when you had that green box and there was like a number on the right?
From this picture?
No. Like when you were using the autocomplete,
Mm-hmm.
there was always like a number on the right, like 8 or something. Like what's?
Yeah, because if you have something like append and you have two holes, these things,
It's just a number.
yeah, it's just numbering the holes. So when you look down here to see what type it is, you can kind of get it. You can also, if you say Control-C, Control-Comma, that will tell you what the goal of the current hole is.
All right.
Oh, nice.
So this will work. It's not particularly efficient because what's happening in a sense is left recursive. You're going to build up intermediate lists just to pull them apart and stick them on the right a lot. So you get kind of this hidden, I don't know if you guys seen that, like, what is it? It's like hiddenly n-squared algorithms or something. Hiddenly quadratic or secretly quadratic? I don't know. Anyway, this is secretly quadratic in the append, and we'll fix that real soon.
Can you scroll up to where you have from list again real quick?
We're going to define that a little later.
Oh, that's not even defined yet?
No, we can do that earlier though. I deleted it, so let's do a from list. So the idea, if it's a binary search tree, the from list is going to need an insert. So let's insert. Say we have a tree and we're going to stick a nat in it. So we're going to stick a P and a T, say. So if the tree is empty, we have a leaf, so we're going to need a node, and the node is going to need three things. It's going to need a value and two subtrees. So we have a value, it's P, and the two subtrees, so we're just going to make leaves. We're going to be doing a binary search tree. I'll call this X. So that means that we're going to need to compare P with X to decide, are we going to put it on the left tree or the right subtree? So the way we do this, if we want to call a function and get a result back and pattern match on the result, we use this cute with construct. So what we're going to do is we're going to use our compare function here up above with P less than X, and then we're going to do this kind of a thing. And then what this says is sort of like, it's creating an extra line. You'll see what it looks like in a moment when I expand it, because it'll fill that back in. But this R is now the result of this. So if we go in here and we say Control-C, Control-Comma, this R is a bool, which is the result of comparing P with X. So if I k-split on that, this is what's happening, is like the with construct is sticking like an extra argument that we can pattern match on now. And since it's a dependently typed language, what can happen is that when you k-split on this, it's going to change values over here, because this result might depend on a specific value over here. And I'll show you that. I'm just giving you like a foretaste of why you would want a construct like this. But what you can do is you can keep on saying with and add more and more kind of results of intermediate things that you want to use to determine your result. So in this case, if we know that P is less than X, then we're going to want to stick it on the left side. So like here, if we have 3 and we're inserting 1, we're going to want to insert the 1 on the left side. So what we do is, well, we're always going to have a node, and the pivot's never going to change, right? Because if you imagine, if you kind of cover up here, we are going to insert the 1 down here, but the pivot stays the same. We're always inserting numbers on the fringe. We're always replacing leaves. So we're going to keep X, and then we're going to recursively insert the P on the left subtree, and we're going to leave the right subtree alone. So I'm using this kind of control space to fill in these things as I type them. And you can do Control-C, Control-F to go forward a hole, and Control-C, Control-B to go backward a hole. So if you're used to Emacs sort of control everything bindings, then you can kind of get it. I'm actually not very good at Emacs at all. I'm just really good at Agda Emacs mode. Okay, so In the second case, we're going to leave the left tree alone and I'm going to insert P on the right side. And now we have insert, and so we can, so if we say like my tree 2 or something, we have another tree, we can do something like this, where we say insert 3, you know, I don't know, insert 1 to insert 5 to insert 3 to nil. Leaf, sorry. Gotta know what I'm calling these things. And so when you look at, when I normalize that, it's kind of run all the inserts and then build the tree how it looks. So when I say my tree 2, Control-C, Control-N, and normalize it, I'm going to notice that I have a node with a 3 at the root, the left subtree is a 1, and the right subtree is a 5. So I effectively have created this tree here by inserting the numbers in this way. All right. So now we can write our to list. Is that what I want to do? Yeah, sure. Where if we have a tree, wait, no, from list, sorry. Mine is going crazy. So now if we have a list, we can turn it into a tree by calling insert like this. So we're going to effectively code this generically, and those, of course, no. So we can case split here. So in the nil case, we're just going to create a tree, a leaf, I mean. In the other case, we're going to insert x into something. I don't know what I'm going to do. Well, we can from list the rest of the x's and insert x into that. So now we have from list, and so if I have some numbers here, I'm just going to copy this over. I just created a random sequence of numbers. Now if I do Control-C, Control-N, I can say from list of numbers, and now I got some gigantic tree that is ordered. Not necessarily balanced, but at least in order. So if I do a from list of that thing, then I effectively have sorted this list. So if I do Control-C, so I did from list of numbers, and now if I do a to list of that thing, I get back a sorted list.
Can you customize the print method? Like if you want to make a nice ASCII tree image or something, could you?
Yeah, I think they added something like that kind of recently, but it's not, or you could, there is a kind of a string sort of primitive that you can write something like with a string and stuff. The strings aren't commonly used, but you can do that. I think most people typically sit around in like abstract structure land and create stuff that way. But for our purposes, this kind of can work. So then effectively, if we want to sort, now we'll have a sort list to list. So if we take x's, what we can do, well, it's easier to not type it, right? So we do a to list, or from list of x's, and then we to list it. So if I say sort numbers, then I'll get the same sort of thing back. All right. So that now we've created a simply typed binary search tree that can effectively create an intermediate, like starting with a list, create an intermediate ordered tree, and then flatten it back down, and sort of composing those two effectively will give us a sort function. All right. I'm not going to give you the optimized version of this, but you can avoid this quadratic penalty by kind of like doing something like a fold. Oh, speaking of folds, let's generalize this from list into a fold, shall we? This will show you a little bit about what how you kind of do parametric kind of stuff in Agda. We're going to just call this fold R and remove all of the tree-like stuff. So, well, in the one case you're going to need a default value for nil, so we're just going to leave it tree for now and add kind of the default value, right? So here. And then when you recurse, sorry, we're going to need to keep passing that around. And then if you hover over something and do like mouse 2 to jump to definition, you can jump right to that. So we're going to need a function that looks like this. So we'll pass that in. Voila. So we're going to call that f. So instead of insert, we're going to call f. And then when you recurse, you're going to have to pass that back. And then now we parameterize it by yet another argument, which is if you have something of type set and you have a function from nat to, you know, take a nat and an x, it'll give you an x, and you have an x, the default, it'll give you an x, not a tree x. And what happened here? Oh, well, so now I added an argument x that I got to pass around to. So this is how Agda does parametricity. We effectively created a dependent type. This is why you can name things in type signatures, because you can refer to that value later. If I have something that's a set, then now you can talk about I have some value of that set over here. And so I'm using, this is the same, all these x's are the exact same set. This can't be like some different set over here, you know, or it totally wouldn't work. So what we can do for sort, instead of saying from list, we can do this full R, and tree is our set, right? Because we're going to create a tree in the end. Here, watch, let's just do it this way. So if we stick a hole in there and we say fold R, we fill in what do we need? Well, it says 1, we need a set. So you could either start with the insert. Say I've typed in the insert. I know I'm going to be inserting stuff, but I don't know what the type I need over here is. If you do Control-C, Control equals, that will say, look at your constraints. Since this is dependent and I have filled in what this is, it knows that this is nat to tree, so it infers. You can't infer general stuff, but it infers a lot of the common things. So it can infer that this x is really of type tree. So that's what it's saying. 1 has to be tree. So it can fill it in for you. And then over here, we're going to give it the default value of leaf, right? And then the x's is what we're going to fill in there. So now we've created a generic full R, which we'll use later.
Mine thinks that first argument after folder is set. It's just like a funny thing. It's probably some discrepancy in my.
Yeah, no, yeah, you gotta stick a set in here. Tree is a set.
So tree is a set? Well, but it says the one after insert is a tree, the one after tree is a list, but the one after folder is a set according to the way this predicts what the form will be. But I don't know. I kind of just mentioned it because it's like a funny like thing of the. It's hard to make it exact, I guess.
Yeah, I'm not quite following. Maybe can look at it later. What you're running into. So if you notice that since I stuck insert here, basically if I'm providing this function, you can infer what the type of this thing is. And so Agda, if you can infer something by unification, which that can be, then if you use curly braces, the argument is still there behind the scenes, but you don't have to keep referring to it all the time, which is pretty convenient. So you can just kind of infer it. But sometimes if life gets bad, you can just say x equals tree and then pass it explicitly. So that way, what you can do is if you know things can be inferred by other things later because you're like using values that are unambiguous, then you can start using these, implicit arguments that will help sort of shorten the code, which I already did here. So now we don't have to keep passing around tree everywhere, and you don't have to pass around the x in this. All right, so now that ends part 1. Now for part 2, which is sort of like the meat of what I want to show you. I want you to come away with at least sort of understanding what's going on here, and I realize that it can be a little tricky to kind of get your mind like figuring out what's going on here. All right, so we're going to put bounds on our binary search trees. That's going to enforce this invariant. So I'm going to show you that we can't construct a tree that this doesn't hold. I can show you really quickly that I can construct a tree here. Didn't we like define one somewhere? Anyway, you can either do one, my bad BST. All we do is, it's right here. There, that was the one I want. See, if I can just stick 5 on the left, no one would notice. And but what I'm going to do is prevent you from sticking the 5 on this side. All right. So to do that, you think, that shouldn't be too bad, right? Well, it is too bad. It actually took Conor McBride 15 years, he said, to come up with just the right type. What can happen is you can have this kind of explosion of proof obligations. And so we're going to take a couple little insights. I'm just going to kind of give you the answer because I don't have enough time to show you different bad ways to do it. I'm just going to show you the right way. And the idea is, one, you can think of bounding your trees by what values you put in them. So you can think of this tree is bounded by 1 on the bottom and 9 on the top. You might call that a descriptive. You're saying, hey, how big are you? And then the type would say, kind of reflect how big it is. Or rather, you should think of types as being prescriptive because that way it's more pragmatic. You're telling it, you need to be this way. And so what we need to do is tell it, you need to be this way. But I didn't say the invariant is a binary search tree knows what its bounds are. I said, this needs to be less than and this needs to be greater than. So we're going to focus on a prescriptive way that will allow us to use the types to sort of tell it what we need it to be and then kind of leave the rest be. Because you always can ask, like, how big are you? And find that out later. But you don't, if you put that in the types, you kind of you'll put yourself in a world of pain. All right, so the first insight here is, well, where do we store the fact that numbers over here are less than the one over here? And you take this insight, if you flatten any kind of binary tree, you'll notice you always get this like leaf node pattern. No matter how you rebalance the tree, you're always going to get this leaf node. And so the insight is that you can stick 1 is less than 2 in the leaf. It's not probably the first thing you might think, but you're going to sort of force that 1 is less than 2 over here and make sure that these are ordered okay. So that way, if I try to put a 2 on the left side here, then that won't let me, because 2 then is not less than 1. So that's the key insight we're going to do. And so it's going to look something like this, where I'm going to expand, I'm going to kind of have a loose bound. So I'm going to introduce a bottom element, which is always less than everything, and then a top element, which is always greater than everything, kind of your terminal, sort of initial terminal kind of object sort of thing in category theory. And in the leaves, we're going to store that, hey, bottom is less than 1, bottom's less than anything, so it's less than 1. And then here, we're going to remember that 1 is less than 3, and then in this leaf, we're going to remember that 3 is less than 5, and here we're going to remember that 5 is less than top. And so that way, if we try to shove this 5 over here and this 1 over here, these invariants in these parts will not hold anymore. So a leaf looks like this. It's bottom and top. So we're going to bound. We're going to say the binary search tree. Its bounds are bottom and top. So you can stick a binary search tree of bottom and top. You can stick anything in it because there's no restriction. And so it only has the one leaf with that sort of trivial evidence that bottom is less than top. When we stick a 3 in there, what we're going to need to know is that bottom is less than 3 in this leaf, and that 3 is less than top on this one. And that way we kind of create this sort of, remember if you kind of push the 3 down, remember that you have this bottom, this 3 in the middle here. When we stick the 1 over here, what's going to happen is we're going to compare 3 and 1, and find out that 1 is less than 3, and remember that in this node here, because remember if the 3 kind of bubbles down here, we're kind of remembering the 3 over here. And we're going to preserve this kind of bottom is less than 1 on the left, and this one stays the same. If you stick it on the right, it's going to look like this. Probably not going to make a lot of sense, but if you kind of remember the idea of flattening it, we're going to store all the sort of proofs or all the evidence that were well ordered in the leaves. And with the loose bounds methods, what that gives us is we are storing the minimal number of proofs to guarantee that we're correctly ordered, because with n values we should have n plus 1 proof, or n minus 1 proofs, which is what we have, n plus 1 proofs here, which is what we have. And we can swap around the nodes to keep a balance and ordering invariant as much as we want, because there's no proof information stored at the nodes. All right, you ready to see what this looks like?
Yeah.
Okay. So first, we need a couple of the things that I just said. We need to add this bottom and top notion. So we're going to create a data type called bound, where we have a top as a bound, and we're going to have the value. So for a specific value, there. And we're going to have a bottom. All right. The next thing we're going to do is we're going to move away from Booleans for our comparison function. So let me find the previous one here so we can kind of keep it on the screen and kind of remember what it looks like. Because we're going to create something that looks very similar to this, but it's not quite. So I'm going to call it less than or equal to prime, because I can't think of a better name right now. And so instead of returning a bool, we're going to turn a set. And so now in type theory, since this is a pretty rigorous implementation of it, we're going to introduce, like if you go up top and you think of bool, you can kind of think of bool, if you give it a name, 2, you can think of the name as representing how many elements you can create of it. All right, so if I have my 2 and I of type 2, right, and I ask, how many ways can you create this? Well, there are two ways you can create that, and that's it. So if you kind of have a degenerate case, 1, which is like your unit, unit is of type 1. And so now there's only one way to create a unit. And if we have a 0, we don't give a way to create it. And so there's no way to create something of the 0 type. You can't have a value. And so these are very special things, and they give us kind of a logic that we can put stuff in the type level, have these kind of dependent types where the 1 represents truth and 0 represents falsity. And if we pass that information along, whenever we see a 0 in Agda, that means we can do whatever we want. We've hit an invalid case, and we don't ever have to specify a value. I'll kind of show you what that looks like. So for this function, what's going to happen is 1 is going to represent truth. So 0 is less than y is 1, which is true. And we're going to do the same thing as we did up here. Let me pull this back down. In this case, this is the false case, so 0. In this case, we're going to do the same thing. We're going to recursively ask, well, what's x less than y? So these look the same, and they're representing the same information. We don't have more information here or any less, but it's shifting how and where and why we're storing that information. Okay? So it's kind of subtle, but you can kind of think of something returning set as kind of returning a structure, and this is the trivialist structure you can come up with. I don't know if trivialist is a word, but the most trivial. All right, so how do we use this thing? Well, let's think if we have some function that takes 2 natural numbers, and we're going to, normally you can have preconditions, right? So maybe we want this really to have a precondition that we should only call this function if x is less than or equal to y, right? And then we're going to return some result. So, well, let's define like a stupid result class. Awesome. You can use like, any kind of characters you want. Well, anyway, I'll just put the precondition up here. Anyway, that's the pragma version. All right. So it's like, well, how would you represent? What do you do? Well, I don't know. So most languages, you do a couple things. You either assume that it never happens, right? Or you just check. So you can, like the way we check values in Agda is with this with thing. So you say x equals y, right? Like this.
Need a space.
No, I need this bar dealio.
Oh, why don't you need that space?
I'm not sure which space you're talking about. So the problem is if I check it and and x is not less than or equal to y, then I've called this function invalidly, right? That was my precondition. You should never call this function, whenever you call this, x should always be less than or equal to y, but yet I have to like write code that deals with the situation that x is not less than y. So you can throw an exception, you can like maybe change the result to be option or whatever. So, but that's in the bool case. So you can kind of never, since the bool is a value, you always have to deal with every value. Agda is a total language, so you always have to deal with every single value that comes in. So
you defined less than or equal to prime, and I thought you commented out the less than or equal. So I'm not sure which one's going to use.
this one is the bool. The prime is like the fancy one. I could call it like stick an S in there for like set or something if that makes that easier.
No, it was just I also thought that you deleted your whole definition of less than or equal to.
No, it's still there.
Okay, cool.
Probably should delete it because then I don't have to keep doing all this weird stuff. Okay, I'll show you the contrasting G function, which is the same thing, except now what we're going to do is have a dependency here. Since it's a set, okay, right? So if I have a function like A to B to C, whatever, A, B, and C, like you think, I don't know, if you start wondering what can you do with a dependent language and a type signature, maybe you can throw some value in here. Well, A has to be of type set. So everything up here has to be of type set. But if you notice, this is kind of a function that returns set. Right? So if I give it 2 values, I get a set back, and that means I can stick it right here because that has a type set, right? So I can say x is less than or equal to prime y, and when that reduces, it will be a set. right? Because this is kind of a function that takes 2 arguments that returns a set. So now if I see g, x, y in this like relationship here, now what I can do is when I start pattern matching on x and y, it's going to sort of evaluate, well, what set is this thing over here, right? Right now it doesn't have any idea. And you can't ever pattern match on set itself. So that's the one sort of kick in the ointment. So you never can pattern match on set, and that's why when we define the full R up above, you can never say like, hey, if this set is really, you know, and kind of like downcast stuff. Can't do that. That's why passing something as a set argument is effectively parametricity. You kind of get it for free in the theory. So if we pattern match on X, what's going to happen is that I'm going to delete this one because I'm running out of room here because I want to show you the real one here. So when you pattern match here, now it can reduce this to 1. Okay, so you can ask it. If you do control, they're like keyboard syntax is awful, but if you do Control U, and then Control C, Control comma, it'll reduce everything. And if you just do 1U, it won't reduce it. So inside here, if you don't reduce it, it's just 0 is less than y. But if you reduce it all the way, if you ask Agda to reduce it, which it will, because then it can figure out that this reduces to the trivial case. So we do still need to give result. You can fill it in. But now in this case right here, this is the one we don't want. This means that we have called G in an invalid case, but when we ask Agda what R is, it's 0. And so the cool thing is if you have a 0 in your context, you don't need to give a value for that. So if you case split on that, it uses this little cute little syntax here, and that indicates that Agda agrees that you have a 0 on the context, so you don't need to do that. It's basically, you're saying that's an invalid case. And that's kind of how we propagate evidence. And in this case, we're just going to do the same thing. Well, you can do whatever you want. I mean, I don't know what this function is actually doing. Okay, so now this is the way that we can, there's kind of a dependency here. This x is really the same value as that one in that sense. I'm going to show you another way. I'm not going to actually use this other way, but this is kind of a data family. And they look like, I'll do a double prime because this is really bad. So now I'm creating this thing. If you look at the signature, they look surprisingly similar, very suggestive, right? Takes a x and y nat, returns a set. Well, this is an x and y and returns a set, and it's this like data family, right? It's not a data type exactly because first you got to give it 2 nats before you get some kind of type or setback. So here what you're kind of defining is this, you didn't really say why this is less than or equal to and this is less than or equal to. But in this, now what we can do is kind of give more reasons why. And then later on we can use the reasons why and pattern match on them. And this is kind of more of a useful thing in more complicated scenarios. So one case is that 0 is less than any. So if you give me some number, then 0 is going to be less than that number. And there's a successor case saying that if you have 2 numbers and you're kind of like, you've already shown me that they are less than or equal to each other, then their successors are also less than or equal to each other. Okay? And now we're going to create the h function, which does this another way. So if we say that x is less than or equal to y in this case, now we can pattern match on it. We couldn't pattern match on this one because there was no sort of structure behind it. It was just a function that we had to reduce by pattern matching on the other arguments that were dependent, that were kind of constrained by each other. So in this case, we have this r, and now we can pattern match on the r. And watch this. This is really crazy. So when we pattern match, we get these 2 cases, right? So when we pattern match here, I didn't give a value for x. I said this side is 0. Well, this now is constrained to be actually 0. This is called like a dot pattern. And so this thing is constrained to be 0 over here. And now when I give a result, notice I only have the 2 cases, kind of like I did here. I only had this case and this case. In this case, so I had to like convince Agda that it wasn't there. And now in this case, there is only 2 cases. So in one case, you have 0 on the for x and y is whatever, and in the other case, you have these other two numbers. You know, they can have values too. But so if you ask what r is, you can kind of keep like asking for more values. But that's another way that you can do it. We're just going to use this previous case because we don't, in a binary search tree, we don't need to really know why 1 is less than or equal to 3. We just need to remember that it is and just maintain that so we don't have to keep worrying about it later. All right. So this is like the step that is like really like, I don't really understand what's going on, but you know, at least when I start to see stuff like this, I kind of like, that's kind of interesting, but it's really sort of subtly strange and I don't really understand why. But I hope that as we kind of use it, you can kind of start to see that what's happening. Okay, so we're going to use it. We're going to create our wait a second. I think we have enough to create our BST. So what we're going to do is we're going to give lower and upper bounds to our BST. So remember in the leaf case, now instead of just being like a BST with no data, we're going to actually give it data because we're going to give it this relationship data. So to create a leaf, you're going to have to prove to me that those bounds are in order. And if that's the case, then I will have granted you that L is less than or equal to U. But the problem here is that we've defined less than or equal to using natural numbers, and I haven't extended that idea to bounds yet. So let's do that. So if I have x and y that are bounds, it's going to keep yelling at me, so I'm going to not have it yell at me anymore. So remember, I kind of said that, well, you can stick an underscore if you don't really care what you call it. Anything is less than top, right? And if you have two values, value x and value y, that means x and y are natural numbers here. Here I'm going to not use the whole because there are too many cases that start happening. But this is going to be 1. This is going to be... Actually here, we don't know. Like we have to like check what x and y are going to be. So we're just going to defer to the other one, to the natural number version. And then we're also going to say that bottom is less than anything. And if anything else happens there, that's going to be false. Okay. So now, given kind of this relationship we've created, we've extended that with top and bottom. Top is always greater than anything. We've kind of preserved this relationship here. Bottom is less than anything. Any other kind of scenarios possible. So if you want to align that up to kind of get a sense of that, some people like to do it this way. I think it helps sometimes, but then is sort of not useful in other times. Okay. So what we're going to do here is require that you have to prove to me that the bounds are in order to create a leaf, but for a node, we're going to have some value. The left subtree is going to go, like if you look here, the left subtree has to go from, like to create something from, this is like the L and the U, the left subtree has to go from L to this value 3, and the right subtree has to go from 3 to the U that we started with. So the left subtree here is going to go from L to value X, and the right subtree is going to go from value X to U, and that's going to give us a BST node from LU. All right. So, what we need to do now is define insert. Insert BST, I'll call it. So if you noticed, I still have left leaf defined up above, and so you can have overloaded data constructors, but you can't ever have overloaded functions down here. It's kind of a thing. Because I think the idea is that you're usually specifying the type of the value that you're giving it, so it can distinguish the values based on the type that you've specified. But when you have a function, it's, I guess, less useful that way. All right, so given a number, we're going to have we have a BST that has some bounds, L and U. That means we need to sort of like say what those bounds are somewhere. Then we're going to get a BST in return, right? Okay. I will go back up to my other insert and just bring that down so we can kind of remember what that one looked like, because this one will look pretty similar. There's a couple subtle points, and there's a little bit of one extra piece we kind of need. Okay, so if we case split on the tree, we either have a leaf, and now this funky x1 here is the proof that L is less than U, so I'll just call that LU. And now what we need to create is a BST of LU. And so what we did up here in the leaf case is we have a node. So if we create a node, then we need the X, because we're sticking the X in there, and then we have a leaf. But a leaf now takes a little extra arguments.
Do we need to have the subscript, or can we just do?
It's creating the subscripts, so I'm going to get rid of them. So I can call this like Y, and this will be either the left tree or the right tree. So you can use them. The way you type them is you do a \_1 or \_2, and then I'll turn them in, or \_0. I don't think it ever gives you 0. Okay, but if you notice here, we need to show that the value X is actually greater than the L here. And we don't have any way to do that, and so we're kind of forced to have that as an extra argument. So we're going to have to show that actually the X fits in the bounds, right? If somehow we're trying to insert into some subtree like 5, but the bounds of the subtree are like from 10 to 20, you can't stick a 5 in there because it doesn't fit, right? So we're going to have to keep passing along the fact that L is less than X, and that X is really less than the upper bound. So now we can fill in, now we have like 2 more parameters, LX and XU, if you want to call them that. And now, when it's asking for, you need to show me that X is less than value X, it's like, voila, well that's what we just kind of required that we need to pass in. In the right case, yeah, it doesn't know leaf, right? So give it a leaf. What does it need in the right case? The right leaf, if you kind of remember here, needs to show that like 3 is less than top or whatever. But we don't necessarily know that we're inserting the top. But it needs to know that the X is less than whatever the upper bound is. And that's conveniently what I have passed in. Okay? Now, so that's kind of what this case up here is. We've created it, and now we're sort of need to manage some of these these relations now. So it's starting to get a little bit like annoying, but that's sort of the price you pay. And if you ever looked at mathematical proofs, they kind of look kind of annoying like that, just because you got to get all the pieces right. All right, we can if you want, but I think just for time I won't. You can like wrap this up into another data type, these 3, and then you won't. But you end up having to split it anyway, because you kind of need to split it and give the different values here, so it kind of doesn't, I mean, then it's a matter of style, I think. So in this case, what we did was we compared P with X. And so if you notice, though, in this case, so we're going to need to store, if say we start with a 3 node and we insert 1, we're going to need to know that 1 is less than 3. But if we insert 5, we're going to need to know that 3 is less than 5. So we're going to need to know, like, given 2 numbers, is like 1 less than, is X less than Y, or is Y less than X? And so that's called a total relation. That given any 2 members of some set, that you can either show that X is related to Y in some way, in our case with less than or equal to, or that Y is less than or equal to X. So I'm going to create a little data type that will represent that. So given 2 natural numbers, you either give me a result where that's less than or equal to, so you have to show to me that X is less than or equal to Y. And the reason why it's parameterized by X and Y up here is because when I unpack the cases, I have constrained the values I'm passing in to be the same, that this x is the same as this x. Because we're going to need to know that, because we're going to need to deal with specific numbers. Or it's going to happen the other way. Y is going to be less than x. So now we're going to have to create a compare function that will give us one of these two. So it's like, we feel like we're defining comparison less than or equal to like 5 times here. But so given any two numbers, we're going to get a total result in the sense that it's going to hold one way or the other. All right? So in this case, so we've defined kind of how this works. So we can actually say, hey, Agda, can you just solve this for me? And like, hey, it can. So we'll just like, it holds the left way, right? 0 is less than or equal to y. In this case, we say, Agda, can you solve that for me? And it says, sure, it holds the other way in this case. 0 is the one that's less than x in this case, so it's flipped. In this case, we're going to kind of, since we're specifying which x and y's we're returning, we're going to have to kind of recursively call ourselves. So we're like 1 plus some x and 1 plus some y, so we're going to compare what the x and y underneath those are. And then this is kind of like weird. In this case, like x is less than y. In this case, y is less than x. And the weird thing is that the successors kind of end up reducing down to that case. So it kind of doesn't really look meaningful. But what's happening is this xy is kind of different than this xy over here, just because. All right. So this gives us our compare function, which is what we're going to use right here. So that way we can get some evidence. Is x less than y, or is y less than or equal to x when we insert this element? So we compare x and y. So we say, well, which way does it go? In this case, x is less than y. In this case, y is less than x. And we're going to insert a node with y. And remember here, if x is less than or y, we insert on the left side, right? So we're going to insert BST. Now we need to pass it a bunch of stuff. And this is starting to get kind of complicated. If you look here, see how these lines are like exactly the same up to that bar? You can actually just do dot, dot, dot there. And that will kind of shorten some of those. So here we're inserting x still. And these are the bounds. I don't know what the bounds are, but we're going to insert it on the left subtree. And the right subtree stays the same. And so here, when we ask it, well, what bounds do we need? Here we need to show that L is less than or equal to x, which is what we have right here. That's kind of what we passed in. And here we need to show that x is less than or equal to y. But that just reduces down to x less than or equal to y, which is exactly what the result of compare was. At this point, it's sort of like mathematical proofs. It's hard to follow somebody else doing it, so you got to kind of work your way into it and kind of understand what's happening. But in the other case, the left tree stays the same, like remember here. On the right tree, we insert BST, and now we got all these like things. Well, we're inserting x still. I don't know what the bounds are, but it is the right tree we're inserting into. And since it's the right tree, we need to show that y is less than x over here. In this case, we need to show that x is less than the top. Because we're kind of splitting it. So here, we have a tree, like this is kind of a tree where L is less than or equal to y, and this is a tree where y is less than or equal to the u bound. And now I changed my things here. And so here, what's happening is, since y is less than or equal to u, we're going to like stick a little x between them. So if you kind of like stick x in here, we're going to stick x. So on the one side, we're going to need y is less than or equal to x, and the other side, we're going to need x equals less than or equal to u. That kind of mnemonic kind of helps me. Yep?
Is there any way to make it more, basically, cohesive or simplify the API for the insert? Maybe refining the bound? Once you have the bound proof, if you create a function with a not from the bound,
Um,
that refines itself. So you don't need to pass on to the inserts. You could do that. Because the only bounds are going to have are correct or are going to be bound in the not if you use a tree already created. So because the leaf has optimal.
Yeah, if you have any ideas, I mean, afterward we can take a look and see what kind of changes you'd like to make to it, or to see if like this valid kind of makes sense to you that it is actually doing the right thing or not. One thing I didn't do is actually try to create a direct instance of the BST. So let's just do that. My BST is a BST, and if you stick bottom and top, that's kind of like any value can be stuck in there. So for the leaf case, we need to show that bottom is less than or equal to top, but that's like trivially true. And so we can just sort of say unit. And if we're going to have a node, so now for the node case, we need to have a tree on the left and a tree on the right. But we start with a value, so say we stick 5 in there. Now we need to show that bottom is less than or equal to 5, but that, well, we have to have a leaf, say. Now we have to show that bottom is less than the 5 in this leaf, which is kind of true. So unit is just sort of saying, prove it, Agda, because we're giving it a constant. So it can reduce a constant at type checking time. On the right side of the leaf, we need to show that 5 is less than or equal to top, which is always true. So it looks like that. If we make that 3, then we can do that same tree. So now if we try to stick something on the left, if we stick another node here with a 1 on the left, now we need to show that bottom is less than or equal to 1, which is true. With a leaf, sorry. Got to stick a leaf over here. You can show that that's true. And on the right, you need to show that 1 is less than or equal to true, and that's kind of that. So all these units that were kind of like floating around everywhere are just sort of like, yes, check that this is true. Yes, check that this is true. If I tried to just stick this 1 on the right side, it won't let me this time. Because it's saying 1 is not less than or equal to 0, and so if you start to ask, why? Well, you need to prove to me that 3 is less than or equal to 1, and if you reduce that using this, both of them are values, so this will reduce down to this thing, and this thing will go way up here, and then you kind of like keep undoing all the sucks until you get effectively 0, you effectively get this case, is what's going to ultimately happen. That's why you get 0. And so that case can actually happen. So if I try to say unit, it's like, no, you're reducing down to 0, but you need to really prove to me that it's the case. So that kind of gives you a sense that it's not letting me do invalid things. And if I do kind of a node on the right with a 5, then it's happy. But if I try to make this a 2, again, I'll be unhappy. So that kind of gives you a sense that this is correct. Now if we do another BST down here using inserts, what we can do is we can say insert BST. Now we need to give it, so if we're going to insert 3, right? So if you never remember, how many arguments does, I think I already defined one, so do 2. If you say insert BST and how many arguments do you need? Well, you need 4 arguments, that's kind of annoying. So I'm going to insert 3 into what? Well, now you need to show the bottom is less than 3. Well, that's true by default because it's a constant that I'm giving it. Agda can figure that out for me. In the right case, you have to show that 3 is less than top. The other case, you have to, you're inserting into something. We're just going to do leaf. And then now here, it's the sort of default leaf case is bottom top because that's what I specified for that main type signature. And that's kind of like, all these units are just sort of saying Agda run whatever type that is. And the type is this. And then this is actually a function, so Agda is going to kind of run that function until it gets a result. And it's either going to be 1, which is unit, or it's going to hit 0, and then it's going to say 0 is not 1, is not the 1 type. So now if we insert 5 into this thing, So we insert 5 here. Again, we have to show kind of all this stuff. We need to show that bottom is less than 5. And then here we need to show that 5 is less than top. So when we're doing constant stuff like this, it's kind of really annoying. But when you're doing stuff like this, you need to kind of do the real deal. You need to make sure that you're passing the right evidence and sticking in the right places and things. All right. So now we have this insert function that's a little annoying because we have to provide evidence, and if we want to use that full R to turn a list into one of these suckers, we're going to need to have a little bit different type signature that will kind of delegate to this one. So if we have insert BST, I don't know, X or something, we have a number. It's going to be nat, and the type of BST that holds anything is the BST with bottom and top. So we have an N and a T. So to do that, we're just going to delegate to the insert the other BST, and now we're going to have to show some evidence. Well, we're sticking N in there, and we're going to stick N in the T. But now what do we have to show? On the left side, we have to show the bottom is less than this N, but that's always true, right? By the way we defined that relationship. So that's going to be unit, and here we have to show that N is less than top. Well, top's always greater than everything, so that's true by definition. And now we can write from list BST, which takes a list and gives you a BST of bottom and top. By calling full R. So it takes the insert BSTX that we have here, and then we got to give it a default value. We can just sort of ask, well, what kind of default values you got? Well, I can create a tree that looks like this, or a tree that looks like that. We just want the leaf case, so, and this is X's. And with Ada kind of equivalence, you can do like stuff you do in Haskell. You don't need to specify the last argument. So now we have the from list BST. We don't have a to list, but we can at least do something like, okay, create a from list BST of those numbers. And that, boom, it created a tree with all the evidence in the right spots. It's kind of like insane, but you know, there. So that created that. So let's write the version of append for this guy. Oh no, okay, so what we want to do, right, so our sort before went from list to list, but there's nothing in this signature that guarantees that that list is in order in the end. So what we're going to do, the sort for this case, is we're going to create an ordered list type that's very similar to this BST, call it OList. So the nil case is almost identical. You have to provide the things at the bound. So what it's going to be is a tree. I don't have a picture of it, but kind of imagine the lefts. You block out all the lefts with just one leaf just to show that they're in order. So it's kind of like this right-leaning tree where there's never a left node. So what we're going to do is inline this left node with this evidence here. So all we're going to do is show that L is less than or equal to X. We're going to kind of inline that relationship. And we're going to keep the right because we need right recursion, and that's going to create an ordered list. So if I try to create my O list, again, the like bottom and top will allow any elements in it. You know, can do Control L and say, hey, what can you throw in this thing? Well, nil unit is going to be kind of the start, kind of the same idea. All the proofs are kind of evidence are stored at the leaves all the time. And then if we do, well, let's call it cons because that's kind of a traditionally, or even add. So if we cons 5, now we're going to need to show something here, and this is going to be the recursive case. So we're just going to assume that it's true. So if we stick 5, now if we try to con something on this guy, it needs to be in order. So if I try to do that, is it going to be happy? Yes, it's happy. But what if I try to do that? No, it's not happy because it needs to be in order. So this needs to be a 3, and then you can do like 1 or something.
Whoa.
So, sorry, not const. Now that needs to be there. So if I made that 10, nope, it's not going to be happy because 10 is not less than 3. Okay? So now we have a correct by construction ordered list and a correction by construction BST. So now we can, what we want is the sort, like BST, goes from a list and returns an O list of bottom and top. So that's what we're going to do. We have some of the pieces, but not all of them. We can, what do we have? We have from list, so we can get an intermediate structure here where if we call some function You can say from list BST on X's. But then we're going to have to fill in what the rest of that is. And it's going to kind of be unhappy, so I'm just going to leave that out for now. And now what we need to do is go from to list BST. If we have a BST from that's bottom top, we're going to need to go to an ordered list of bottom and top in this case. But there's no particular reason why those have to be those bounds, so we can just give it any old bounds we want. So, again, those two bounds, blah, blah, blah. So there's our tree. So how do we do a to-list? We did something similar up here, right? With our tree. Where was it now? To-list, this guy. So we have these two functions. I'll bring them back down here so that we can refer to them because, again, they're going to look kind of similar, but now we have to manage the bounds. So in this case, we're going to do a similar thing. We're going to do a hiddenly quadratic function, just because looking at the time, I'm not going to quite have enough time to do all the things I was hoping to show. But I can at least show you what it looks like briefly. So we're going to case split on the leaf, on the tree, and so we get the same two cases, but now we have a little more information, right? The leaf has the ordering information that L is less than U. Here we have a tree that is bounded on the bottom by L, but on the top by X, and here we have a tree that's bounded on the bottom by X and on the top by the U. That's the top of the whole thing. Okay? So what do we do? Well, what do we need over here? Like, can we fill it in? We say Agda. So now Agda's thinking, it's like, well, I'm going to think about this a little while. Can I fill it in with what I've got? Well, after 5 seconds, sometimes it's like you can keep on trying bigger and bigger things, but they never work. And so that's kind of what Agda's doing. It's like, I keep on trying bigger and bigger things so they work, but it actually found a solution pretty quick, which was nil of LU, because it's the same idea, right? An ordered list has to have the evidence in its nil case, which is like a leaf. So in the two-load case, what we did is we created this append of two ordered lists and then sort of stuck the P on the right side and then appended them together. So let's create an append for ordered lists. Now this is where we're going to get ourselves into a little bit of trouble. So, O list or something. If we have an O list of for LU for some bounds, let's do LN, right? And then we have an O list that goes from N to U. Then we should like be able to join them together to get like one that goes from all of them. But we have to give L and N and U, and they're all going to be bounds. And I did something wrong. I did the comment the wrong way. All right. So now X's and Y's. So if we split on X's, just like the append up here, what do we have? Well, nil. Nil we're showing on the left. Remember, L goes to N on this first one. In the second case, we're going to have this X1 is kind of, what is it? I mean, let's double check. Well, here it shows that L is less than X, so we'll call it LX. And this X's here is an ordered list that goes from X to N. So, well, I'm not sure that's important, but okay, here. Okay, so here's the problem. If we want to create the Y's case, what we need is an ordered list that goes from L to U, but all we have is an ordered list that goes from N to U, and this kind of evidence that L is less than or equal to N. But so if we had transitivity, we could like sort of add transitivity and like apply a transitivity thing and have this like intermediate thing that would apply that, and that would work. But it's sort of like, well, we didn't need it to begin with to create the thing. Why do we need it now to append two of them? Like, we shouldn't need it. It should just sort of magically work. So what we're going to do is we're going to be a little bit clever with what we pass in as the second argument. So it's not going to be quite append anymore. What we're going to do is, if you can show me for some m, so like say m is some bound, you can sort of give to me a that m is less than n, or supply, then I will give you a list from n to u. And that way we're kind of like delegating like the problem off to somewhere else, because eventually we're going to hit this case where we have that evidence and we can just give it. So now this is kind of this funky F deal. And if we look at what we have, F takes M related to N and oh, sorry. Goes from M to U. Okay. So here we're trying to get from L to U, and we know that L is less than N, and for some M we can show that L is less than N, like that value is less than N, then we can get an O list. Well, if we apply F to the Ln case, that means M here is going to be L, and that L is less than N, and that means we can create an O list of Ln. So voila, we kind of like have sort of circumvented the problem by adding a little, I don't know what I want to call it, a little bit of sort of like continuation passing kind of thing, like defer till later until we can really give it the thing we need. Because we do have that. The cons case, we cons x onto kind of the recursive case, right? So we're going to append O list onto x's here. No y's. Wait, this is the f. This is the funky f deal. So now in here, what we need is that L is less than x, and we have that right here, Lx. And here what we need is this like crazy function that we somehow cleverly came up out of nowhere. In the paper he shows kind of a little bit of the process of some of the intuitions he had to give that, but I kind of don't have time. I'll just show you like the answer and that it works. So, but it's asking for the exact function that we have, and so voila, we have like solved the type problem there. So, if we use this down here, what in the world would I call that? O list or something? So on the left, what we need to give it is, so here you see we're kind of recursively calling the toList. So let's do that, toList BST, and then what we need to pass it is the TLX case. On the right, we kind of cons the P onto this recursive on the right. So let's do that. I'm confused. Oh, right. Well, the thing is we need to, now we're doing this funky function thing because of append O list takes a function. And this thing here is mx. And now we need to give it an O list of this. So, I mean, it's kind of the same idea. We're just going to cons inside of here. We're going to stick the x on the front of, there's some bounds there that we got to give it. Do we have those bounds? It's asking for m less than x, and we have that, mx. That was the parameter for a clever function definition. And now we need to recursively call toList toList BST on the right with TXU, which is the right side. Voila! Okay, now we got toList BST. So we got everything we need, right? And we're kind of running out of time. And I do want to take, so I only got to part 1 and 2, but I do want to at least show you what part 3 looks like. I won't be able to code it. And then just show you very briefly what the universe kind of thing looks like. All right, so what we do here, well, we're going to list BST on something. Woo. And now we're going to from list, did I call it from list? I don't remember what I call it now. Yeah, from list BST of x's. Voila! Now we got our sort BST. So we start with just an arbitrary list and of numbers, and we create a correct by construction BST, and then we flatten it into a correct by construction list or ordered list. So now if we run this sucker, say we say sort BST, and it takes untype the regular list that we started with, so we can use our numbers, and voila! Now we have an ordered list where all those units are saying yes, these numbers are in order. So it goes all the way down to the end there. Cons 50 with a bunch of parens, looks kind of like some crazy list thing. All right, so that was kind of the goal, because stuff like quicksort, if you think about it, you kind of have this pivot, you got to pick the pivot, and then you got to recursively do the left and the right subtrees. It's sort of similar in a way to just doing what we just did here, whereas we just insert all the elements, and that is having a pivot, and it's like keeping everything sorted as you insert it, and then like flattening it. And the nice thing is that in the end, we have a correct by constructor ordered list. All right, so now I won't do any more live coding, but I will show you code. So 2-3 trees. If we insert a 4 into here, what we allow now is we allow a node to have 2 values. So, and this thing needs to be, everything here needs to be less than 1, everything here needs to be greater than 1, but everything, of course, all of these need to be less than 3. Well, this one, stuff in here needs to be less than 4, stuff in here needs to be between 4 and 5, and this one needs to be greater than 5. And that's how the values, and that's why it's called a 2-3 tree, because every node could either have 2, it's kind of like a double or a single, or like it can have 2 or 3 children rather. And we're going to add one more invariant, and that's going to make sure that we have always a balanced tree. And that is, for a given node, 3 in this case, the children always have to be the same height. So I'll show you kind of how that works with when you add more. So if I add a 6 up here, so this is going to, when I add the 6, this is too big, but I can't just add it as a child down here, because then the height of these children won't be equal anymore. So we have to choose a different solution, which is to bubble up and kind of restructure a little bit. And now if we add a 7, well, the 7 can fit in a 3 node now, but if we add an 8, that's going to bubble, that won't fit down here because we'll have an unequal height tree. So we're going to need to kind of bubble at least a value up here and kind of balance. But if we add a value here, we can't just add it as a 3 node here. We're going to have to rebalance and like shift stuff down here and rebalance down here. So we end up with a nice balance tree of all nodes of 2. All right, so what does that look like? So what we do is we add, oh yeah, here, let's shrink this. I don't need that as much. So in our BST, if you remember, this is what our BST looked like that we wrote. We have an upper and lower bound. We store the evidence that the bounds are ordered in the leaf. And then we have left tree is bounded, is split by x here. So we're going to kind of propagate the value, but now we're also passing this height. So a leaf has height 0, that's like the third argument, and we still maintain the evidence. So for node 2, given a specific height, and given kind of the value, the left value is going to have the same height as the right tree. So this and these h's here are the same h. So those have to be the same number. That enforces that those heights are the same. And this is basically the same as the BST node here otherwise. Also, but if you have 2 nodes of 2 children of height h, well, the overall node now is going to be 1 higher than that. So that's kind of how we define how the h grows as you keep adding nodes. The 3 case, we just have 2 values. So the left goes from, the lower to x. The middle is going to go from x to y, and the third node is going to go from y to u. And all those 3 are going to have the same height. And the resulting tree is going to be 1 higher. When you insert now, what's going to happen is, since you have this height propagating around, you're going to get either when you insert the value, the height's going to stay the same because it fits somewhere, or else it's going to be just a little bit too big, in which case you're going to have a kind of like 2 nodes that are the same height split by some value. That's effectively like, a 2 node. And so the type of insert here is where I stuck those 3 parameters, the x, the one bound, the one relationship and the other relationship. I just wrapped those up into an interval here, into a little data type. It's just like wrapping them into one. It's not really that different. But then what happens is the cases get complicated, because when I compare p to x, so if I'm trying to insert a p into this node, well, I have to see if it's less than, I'm going to insert it here, but if it's greater than, I have to insert it here. But now when I insert it on the left, I get 2 cases back. Either it's good, in which case I just stick it in, or on the other case it's too big, and you have to like renegotiate all the different ranges. But watch this. So the cool thing is, since everything's correct by construction, what we can do is ask Agda, hey, can you solve this problem for me? And so what Agda does, if you pick all these cases on the right, in each case, and you ask Agda, it either gives you the tree you started with, if you notice that's the same as this, and that's because there's no relationship between the value and the types that I get a value and that there's anything in the result that says that value has to be in there. So there's nothing in the type preventing that from happening. Or you have a correctly constructed resulting tree down here. So you can just say, hey, I want the one that has my value in it. And you can fill it in. So that's kind of how I fill all these things in. I'm just sort of saying, doing the high level work, and then even like this case, this interval, remember I had to like fill in like which thing do I need? Is lx less than x and lx than that? But you can just say, hey Agda, can you like solve that for me? And it's like, sure, this is what you need to put in there for it to work. So it just fills it in and kind of propagates all that. So I did those in those cases. When you have a node 3, that means there's 3 children. So this is where the rebalancing happens. If you insert into like p of x, that means you're going to insert into this first one. If you get back something of the same size, you can just swap it in. But if it's too big, what happens is you get 2 trees, but now you have to kind of rebalance them. They're kind of this case that we ran into here. Both of these cases, in fact. Like, see here, we're going to need to go from this to this. And those are quite different. Like we have to reshift the left side and the right side. And it's 2, 3 trees and 2, 3, 4 trees, which are similar, but with a 4th node, one that can have like 4 children. They're typically pretty hard to get right, because look at all the information that I have to put in the right spots. It gets kind of complicated. But since they're correct by construction, I can just say, hey Agda, can you solve that for me? And it's like, yes. Here's the tree you started with, or here's the solution where now you have turned a node 3 into 2 node 2s, which is kind of what happened here. I had a 3 node on the right, and now even a node 3 up there, and now it kind of rebalance them into all 2 nodes. So I can say, hey Agda, give me that one. And voila, fills it in. This flap thing is kind of like flatten and append, or kind of like from list and append together. And the only difference between this and the other one is that instead of having a list on the left, we just have the tree on the left, and we kind of just propagate the same idea. We have this like funky bounds function. And then the results kind of look like a fold R, where you're like, everything's recursively calling, and it's all kind of balancing off to the right. Right, for you it would be this way. And that way you don't get this nested quadratic, because you never build up in your intermediate structure on the left and then tear it down a lot. And so in the end here, you kind of have the same thing with the sort 2, 3, you run on the numbers and you kind of get the same thing in the end. But if you notice, all those structures look really similar. So what he did in the paper is like, well, let's just try to generalize all these kinds of structures. So if you start from this kind of universe way of imagining data types, where you either have a recursive structure, kind of like a list, you have the nil case, but in the cons case you have this recursive substructure, or you have a parameterized thing, so like a list takes a parameter with some type, or you have a leaf, or you have like an alternation case, so lists are either a leaf kind of thing, like a 1, or a recursive substructure, and then you can have a product, so that well, a list on the recursive, so it doesn't recurse only, which would be more like a natural number. It would actually have a value and recurse. So if you type like a JJ list or something, will look like this. A list is either a 1 on the left, kind of like a leaf, or it's a it has the parameterized value, kind of with, like a tuple along with a recursive substructure. And then what you can do then is define, like, turn this like weird kind of structural notion of what a list type looks like into an actual Agda set, and with this kind of recursive knot. So it's kind of weird. This is like super highly parameterized, but what you can end up doing is like the mu j is sort of like a list type. So if I wanted to have a list value, what I say is, given a mu jj of this jj list that I defined above, and it's parameterized by natural numbers, because that's what I'm going to stick in there, then what I can create, the nice thing is you can sort of ask Agda, well, what can you stuff in that thing? Well, if you think, this is sort of like the empty case, where it's an empty list, and this is a case where you stuck a 0 in there, and this is a case where a list where you stuck a 1 in there, and you stuck a 2 in there. So what happens is, I don't know, it's kind of weird, but you can define, this allows you to define this kind of really simple looking structure, map it back to Agda using this sort of like complicated thing, and that way you can talk about generic types. Because this is a list, you can define a tree. A tree would look like a binary tree, is instead of on the left being a leaf, it's actually the recursive substructure. So you'd have you'd either have, well, the leaf is of course there, but then here you would have both a parameter, like 2 parameters, right? One where you have a parameter on the left and you have a recursive substructure on the right. And so that way you can kind of define this universe of data types. And this is kind of where you like really go on the rocket ship and blast off into abstract land, because if you're not used to this kind of thing, it's just like, this is like totally insane. But what you can do is, this star is what we're going to kind of slightly modify into, and you can create a traversal, given an applicative of something, you can kind of create this traversal sort of structure which kind of like flip-flops in, right? You have like an A to H of, if your H is your, so A to H of B, and you have this funky structure, you'll get an H of that funky structure with the inner type sort of swapped out. You can create a fold over any structure. So all these different structures, you can like call fold on them all the same way by defining this kind of monoid over function composition. And so you can like shrink it all into one piece. So that way, when I create all these different ordered universes, I can just reduce them down into this and like shrink them all down, or kind of build them up rather into these ordered structures by creating the insert function. So here's the ordered version. Is what I did is I take away the parameter, because the parameter now is kind of like the value you're sticking in, whereas like in a list, the parameter of a list is like a natural number or something. So if you have a list of numbers, you're sticking numbers in all the nodes, and that now becomes a pivot. So here, when I pivot, what I'm saying is, well, here's a node, and there's this kind of pivot structure where you have a value, and everything on the left has to be less than it, and everything on the right has to be greater than it. This doesn't enforce the invariant, but this expresses the idea of the pivot. And then he refines that a little further so that we create the bounds on that structure. So now it's bounded. And then we go even further down below where we can allow an extra index. Like in the 2-3 tree, we kind of added an extra index for the height, and that would enforce the height invariant. And so now we get something where we have this data type where we can create any ordered structure where all the elements are by definition ordered. And this is what an ordered list looks like. It looks like, well, it's either a leaf kind of situation, the nil case, or we have a leaf case here, but pivoted. So here, remember all in the leaves, we're always storing the bounds. So this has a bound over here, and this is going to have a bound over here, and then we're going to have a right substructure. So this is going to kind of create like this, well for you, like this right-leaning tree, which is the same ordered list that we defined. This is what a tree looks like. It's just you have the recursive substructure on both sides. So that's this binary tree. We can create an interval, so given a value and then these two like relationships, which is, you notice we always pass the insert. A value and like two relationships that express that that value fits into that bound. That's what this interval will express. We can create a vector. A vector is like a list indexed by its length. So this is an ordered vector indexed by its length. And what you can do is, since you pass in this extra index, so the 0 case is just going to be a leaf, but in the successor case it's going to be a leaf with an order in it and a recursive substructure, and you keep on recursing down until you hit 0. So now it's indexed by its length. And you can even do really funky things because we added a 0 case. Remember, if you ever hit a 0 set, that will like rule that case out, so you never have to deal with it in your code. So here we create ordered vectors of even length. So now you can only create a vector of like 0, 2, 4 size. And so that kind of gives you some flexibility there. And you can create a 2-3 tree. So this is what a 2-3 tree looks like. In the leaf case, you just have a bounds. But in the when you actually have a node, so it's at least one big, you're going to have a recursive substructure on the left of a certain height, right? So all these h's mean all these recursive substructures are the same height, but pivoted on the, and then here what's going to happen is it's either going to be just the 2 case, so here everything is ORed in the middle. So in the left case you only have one more node, which in this case is a 2 node, or you can have 2 more nodes, in which case it's the node, the 3 node that has 3 children in it. And then you can define insert using all that structure. It's a little bit wonky, but pattern synonyms in Agda are really nice because not only can you kind of create this pattern for this kind of more complicated artifacty structure, but it also satisfies the completeness checker. In Haskell, the pattern synonyms don't actually satisfy the completeness checker, so you kind of like have to fake it or have an error case. And then we can create the same sort of insert, and now what you can create a sort, but it's a subtly different. It's not just a list to an ordered list that goes through the 2-3 tree, but it's any data type parameterized by one type, one sort of thing. So like if you have like a list, not just a list of nat, you could have like a maybe of nat, or I don't know, a binary tree of nat, or whatever you want, and it'll take that, build a 2-3 tree, and then flatten it down to an ordered list that's correct by construction, all in this one line. So this fold R kind of like builds up that structure from anything, and you can flatten it back down. Anyway, any questions at the end? That's all I have. So if you're like me, when I have played around with Agda, it's like I follow along really well for the first little bit. And the second part, there's this weird thing that happens. I didn't know what happened, and then I get kind of lost. And then everything after that sounds cool, but I have kind of lost the ability to track it. So I kind of assume that that's what's going to happen here, but I at least am trying to like show you what this kind of code kind of feels like with something that's a little more tractable with binary search trees and stuff. So thank you.